Yeah, it's same kind of guy. Let's talk about some reactions of 5-membered heterocyclics before going to 6-membered heterocyclics. We have these examples here. This is pyrrole. As we say that for the 5-membered heterocyclics like pyrrole, thiophene, and furan, for them, they prefer position 2 or the alpha position. This is alpha, this is beta. So they prefer position 2 than position 3. Also this one, alpha and beta. So this reaction of pyrrole with acetyl anhydride with ammonium chloride, we shall form this as a major product. We shall form this as a major product. We saw the resonance structures that this one is more stable, forms a more stable cation. This one, now we have an electron withdrawing group, here at the nitrogen. So this one will affect the nearby carbon atoms. So they are electron deficient than the carbon at position 3 or the beta position. Therefore, if you have electron withdrawing group at the nitrogen, the preferred position will be position 3. Will be this position, not position 2. Also, this reaction, nitration of pyrrole, to also occur at position 2, shall have NO2 at position 2, because there is no electron withdrawing group, and position 2 forms the more resonance structures or the more stable carbocation. This is acetic acid. We prefer weak acid. It is a weak acid. We prefer weak acid than strong acid because of polymerization. For example, if you have a strong acid, this position 2 is very reactive. We shall form this structure. Remember, if you have a strong acid, this one will attack the hydrogen, and this nitrogen will try to stabilize. Before this one, as this one attacks, it would use these electrons, the bond pair electron. Now this one will be plus. If it becomes plus, now this one will try to stabilize this carbocation, and this one become plus. So nitrogen will try to stabilize this carbocation. So we shall be having this. We form a bond here. Then here we have gotten our hydrogen ion, and we have formed a bond here. But this nitrogen is plus. It is plus. So it will try to regain its stability. As it gains its stability, this one will be plus. We shall form a carbocation. So another pyrrole structure will come. So this will be acting as electrophile. So we shall form this. Then we have this. Now here we form this. Also, this one stabilizes this. Then nitrogen stabilizes this carbocation. Again, we form this one like this. Here we have this bond. Okay, this bond is taken by nitrogen. So we shall have this, then a bond. As this one again gains its stability, again another one will attack. So we shall end up having a long chain of pyrroles. We shall have a long chain. So when it goes, another one will come like that. This one attacks this carbon. Again, this one stabilizes. This one stabilizes. So we have this hydrogen. Of course, there are two, but I'm representing only one. I'm showing one to show that this was the one which was gained, but we have another hydrogen here, which was there before. So we shall have this with this NH with that bond. Again, we form another one, H with our bond, like that. So the polymer continues growing. That's what we shall have in case you use strong acid. Strong acid. That's why we use weak acid. This is acetic acid. Now, we have this one. We are going to do the mechanism. Now, we have a dimethyl. It is N dimethyl amide. This is phosphoryl chloride. This is water. So, this reaction also, we shall have a substituent at position 2 or the alpha position. Now, how can we do the mechanism? Phosphoryl chloride, this is the structure, shall have this with chlorine, and chlorine. Then this one, we are having this N-dimethyl amide. So, chlorides are good living groups. As this one goes, oxygen is having lone pairs of electrons. So, we shall form this with chlorine, then oxygen is attached. It is still having its two bonds. So here it is, hydrogen, N, and methyl groups, but it's now a plus. It is a plus. So nitrogen is having lone pairs. As it forms a bond here, this one, oxygen stabilizes. So we shall form this. Then here have oxygen with now a single bond. With a single bond to this carbon. Then you have hydrogen, and we have formed a bond here, and it is plus. This is what we have. As N tries to stabilize the chloride, this chloride, it's now a nucleophile will come and attack this carbocation which will be formed. So we shall form this. We have a P, a chloride, okay, and a chloride. We have oxygen, the chloride here, N will be having its lone pairs back, and a hydrogen here. Yes, that's what we are having. Now, as this one forms a bond, this one will go off. It will go off. So we shall have this. Let's put it this side. So we shall have a P. It has gone. So we shall have N with two bonds and is having a chloride and a hydrogen at this carbon. Then with two methyl groups. This is what we are having. Now, as it takes its bonds back, then pyrrole will come. So this one will attack that carbon. So when it attacks the carbon, of course we shall have resonance. This one moves, then this one stabilizes that. So we form this. And it's now plus, it has formed a bond here. Here we're having a bond. Then H, we are having a carbon, this carbon here, this carbon. Then there is a chloride and hydrogen plus N with two bonds. That's what you're having. Now, nitrogen is having its lone pairs back, so it will form a bond here. Then this chloride goes. So we shall have this. This is plus with a hydrogen. Then here we're having nitrogen with double bonds. Then we have hydrogen here. Then N, this one is plus. So this is what we are having. And remember, we have a hydrogen here. There is a silent hydrogen. So this one, nitrogen, will try to stabilize. It brings the bond back. Then we shall form a carbocation. Then this bond forms a bond here using the electrons we are having here will form a bond here. Then this one will be plus. So to stabilize this hydrogen will be lost. Form a bond there. It's lost, can be taken by the chloride, which was lost. So this one takes it. So at the end, we are having this structure. Nitrogen, hydrogen. Now we have formed a bond here. Also here with a double bond. Okay. And nitrogen with two methyl groups and hydrogen. So this is what we are having after addition of phosphoryl chloride. Then water comes. We have this N with double bond, nitrogen, and two methyl groups with hydrogen. Then water comes. As this nitrogen takes its bond back, this one will attack the carbocation. So come up with this. Come up with this. And like this with like that. So this nitrogen will take the hydrogen. So we come up with this hydrogen, double bonds, then N the hydrogen. So it's now plus. Then you have OH. So this one forms a bond. This one breaks off. So at the end, we form this NH with O. Remember, we have hydrogen. This hydrogen here is still there. It is there. So we form a bond like this with H. This one is plus. Then hydrogen will be lost. So form our structure like this. With OH at position 2. So that's the mechanism for reaction of pyrrole with an dimethyl amide with phosphoryl chloride. And the reaction occurs at position 2. Also, what is added as a secondary reagent. Yes, same the guy. Let's go to reactions of the 6-membered rings. 6-membered heterocyclics, we have pyridine as an example here. Remember, pyridine is having a lone pair of electrons which doesn't participate in resonance, so it's available for reaction. Though for aromatic substitution, it will prefer position 3, but instead, since this one is more reactive and the lone pair is available for reaction, it will prefer this position than aromatic substitution. So instead to have addition reaction, so we shall form this ion. Instead of nitration, so we shall not have nitration. So this is the major product, will be the major. This one will be there but very little, since the lone pair is available for reaction and it's not part of the resonance. It is localized on nitrogen. So this one will be the major product. Also here, same thing. Instead of acylation, we shall form this. Then here we shall have that instead of this one will be very little. So instead of acceleration at position 3, or the beta position, this is alpha, this is beta, this is gamma, alpha, beta, then gamma. So this one will be the preferred position because the lone pair is available and it's localized. Now here you are having methyl groups at position 2. This one, they create a steric indifference. So for reaction here, instead of having a reaction at nitrogen, we shall have a reaction at this position here because you're having a space. Of course, the angle here is very big than this angle. So this one will create a steric indifference. So the major product will be this. You're having this nitration reaction. So we shall form this as a major product. We have this structure. You can try it out and get the major product. We talked about indole as the preferred position of electrophilic attack. So you can try it out.